So now there's no echo. Okay, yeah. So now there's no echo.
Okay. Can people on Zoom hear me? Okay, perfect.
Yeah, we're like, it's on YouTube, right?
Okay. So they can hear us. So maybe let's start. Okay. So let's start. Today, it's our great pleasure to have Alex from Boston University, and he was a student in Claudia Tremont's group, who had done pioneer work on quantum many-body scars and Hilbert space fragmentation. And today, he will talk about group work problem as a framework of ultra-slow thermalization and fragile Hilbert space fragmentation. Right, welcome.
Yeah, thank you. So, yeah, today we'll be talking about glassy and non-ergodic systems. So I was thinking of what to, put on the introductory slide for this. And as I was thinking about it, I was drinking tea. So that's what came to my mind. Typically when we think of a StatMech system, generic typical systems, they are ergodic, meaning that they explore the whole available phase space or Hilbert space, and they also equilibrate fast. So let's see this in action. So you see the state quickly becomes from a kind of complicated state with some structure, non-trivial structure, it quickly becomes a boring state where the milk is mixed in the whole entirety of the cup. Now, let me show you the next examples. So some systems, they still might be ergodic, so they still explore the whole available phase space, but they equilibrate very slowly. We usually call such systems glasses. So here you can see that, the milk is slowly seeping into the bottom part, but this process happens on a much larger time scale. And if I skip to the end, you can see that eventually the state still again becomes kind of like a boring state, boring typical state. So yeah, this behavior is usually, we can observe it in regular structural glasses and spin glasses, and then many-body localized systems. I put a question mark there because there is still a lot of debate of whether this is a phase of matter or it's just some kind of pre-thermal regime. So let me show you now the third option. So some systems might be non-ergodic, meaning that they actually don't explore the whole available phase space to them. So, and here you can see that the milk actually does not go to the bottom part of the cup. And so such behavior we can observe in systems with symmetries. When if you're in a particular symmetry sector, then the system will not go into other symmetry sectors. And in integral systems, when we have too many symmetries, essentially that completely define the behavior of the system. And then there are more recent kind of exotic phenomena such as Hilbert space fragmentation and quantum many-body scars. And again, I put the MBL systems with a question mark here. So now the question that we ask is, can we somehow engineer systems with desired thermalization properties? So maybe we want a system to thermalize slowly, or we want the system to thermalize fast, or we want to make it ergodic or non-ergodic. And this is where our project comes in. So let me introduce the team. So this project is mainly driven by Shankar and Ethan. They are students. So Shankar is a student at MIT, and Ethan was at MIT as well. Now he's at UC Berkeley. and also with Sarang at Princeton. So the answer to this question is yes, we can actually use some math, in particular geometric group theory, to construct quite a generic family of models, which possesses almost, we can kind of engineer almost any desired thermalization properties, making them ergodic or non-ergodic, and with almost arbitrarily thermalization, including arbitrarily slow thermalization. And I will explain you later what this means.
Just a basic question.
Yep.
When you say thermalization, do you mean thermalization of the state or all states in a given Hilbert space, or a subsystem of a system?
Yeah, you can talk about both notions. So you can talk about the worst case scenario. So you can ask whether there exist some states in your Hilbert space that would thermalize for a very long time. Or you could ask what happens to a typical state. If I initialize my system in a random initial state, would it thermalize quickly or slowly?
So here are you talking about the typical states that you're most likely to encounter if you are going to the company state?
So I'm talking about both. So you can cook up systems where the worst case scenario, only the worst case scenarios thermalize slowly, but you can also cook up examples where even a typical state would thermalize for a very long time. So here's the outline of our work. So we use something that's called a group word problem. It's a problem known in complexity theory. And we use it to construct a class of models where the resources that the system needs in order to thermalize are kind of defined by the choice of the underlying group. And what do I mean by resources? So there are two types of resources we distinguish, the temporal and the spatial resources. So the temporal resources roughly means how much time it takes for the system to thermalize. And we can achieve almost arbitrarily large thermalization times. So we can make the system scale the thermalization time to scale polynomially with the system size, exponentially, iterated exponential, or basically any function you can imagine. Then I also want to kind of point out that this glassiness occurs at 0 temperature, and it does not require energy barriers, disorder, and it has nothing to do with localization in space. And then in spatial resources, so what spatial resources means is how big of a bath the system needs in order to thermalize. So sometimes if you confine the system in a finite space, then it cannot thermalize. But if you temporarily extend your system, increase its size, and let this kind of jammed state to expand into this extra space, do some dynamics there, and then contract back into the original space, leaving the rest of the space in the original state, then it can actually thermalize. So sometimes the system needs a bit of extra space in order to thermalize. And again, the amount of this extra space we can make it scale almost arbitrarily with the system size. And it's also nice that geometric group theory actually allows us to prove these bounds analytically rather than just observe them numerically. So what's our main strategy? So in order to thermalize, the system needs to explore the whole allowed Hilbert space. And typically, if you have L degrees of freedom, your Hilbert space has dimension that's exponential in L. But usually, this Hilbert space is well connected. So in this graph, vertices are states in some chosen basis. So say I choose a product state basis. So vertices are just product states. And then whenever you see an edge between two vertices, it means that the Hamiltonian has a non-zero matrix element between these two product states. So typically the Hilbert space of a generic system is very well connected. So if you ask the question, what's the shortest distance between any two randomly chosen product states, it would be of the order of L, although the number of vertices is exponential in L.
How are you defining the distance between two states?
Oh, just the number of edges So for example, what's the shortest distance between this guy and this guy? It's just 3, 1, 2, 3. So
How are you arranging the space in the first place?
the position, sorry, what's your question? The position of vertices does not matter in space. It's just the graph that matters.
How are you placing one state into one node of the graph?
Oh yeah, so the vertices are product states. So suppose you choose a basis, and well, usually a convenient basis is a product state basis. So suppose each vertex is a product state. Now, whenever you see an edge between two vertices, it means that the Hamiltonian has a non-zero matrix element between these two product states. So our strategy is to change the connectivity of this graph. So our models will have a significantly different connectivity, which looks more like a tree rather than like a well-connected cloud, such that the typical distance between two states in this Hilbert space will be much larger than L. Okay, so how do we do this? So for this, I will have to kind of divert from physics for some part of my talk and just dive into some geometric group theory. So let me define, let's take a discrete, finitely presentable group. And typically people write it like this. So G is the group, and then this capital S is a set of generators that generate this group. And then the R is a set of generating relations. And maybe let's look at some simple examples like the groups that you probably all know. So for example, group Z, a group of integers, is just generated by a single generator, and there are no generating relations. So if you multiply A by A, you get a new group element, and if you multiply it by A again, you get again a new group element. Now, on the other hand, if you want to define a cyclic group Zn, then you need a single generating relation, which says that if you raise A to the power of n, you get back to the identity element. Now, if you, for example, the group Z cross Z is now generated by two generators, and the only relation that you require is that they commute. So you write that xy is equal to yx. Or similarly, we could write it as xy, x inverse, y inverse equals identity. And I just wrote another example, which is the group D4, a group of symmetries of a square. Is generated by two generators. Again, this is a rotation by 90 degrees and the reflection. And you can see the generating relations here. For example, this one tells you if you rotate by 90 degrees, then reflect, rotate again, and reflect again, then you should get back to the identity. And of course, if you reflect twice, you get back to the identity. And if you rotate by 90 degrees 4 times, you also get back to the identity. So here I just wrote some mock groups. So these relations don't really mean anything. It's just to demonstrate the concept. Now let me introduce a word. So a word is just a sequence of generators and their inverses, just written one by one. So it's like a string. Now there is a homomorphism from words to group elements, which is very simple to understand. You just look at the word and you multiply all the generators one by one, and you get some group element. So it's a homomorphism. So it's a map which is many to one, because there might be lots of words that multiply to the same group element. And so let's see, for this mock example, let's look at our word. So first, let's try to figure out what it's equal to. Let me first introduce what's a group word problem. So now if I give you two different words, and I ask you the question, do they correspond, do they multiply to the same group element or not? That's called the word group word problem. So let's try to solve the group word problem for this mock example, W. So first, note that this relation essentially means that A and B commute with each other.
One basic question.
Yeah.
So when you are mapping this, the words to the group elements,
right?
then there's a starting element on which it acts. They are all acting on identity.
They all, they all act on identity.
Okay. And I just want to ask is this actually invariant of what your starting element is? Does it depend on what element you start with?
Sorry, what do you mean by what element you start with? So this homomorphism just literally means you take these generators and you multiply them together.
Yes, and you get a matrix. So these are matrices. And if as a matrix it works on a state which is a vector, so you need first have
okay, so you shouldn't, first of all, you shouldn't think of them as matrices because not every group has a representation. So only if a group has a representation, then you can think of them as matrices, right? And some representations might be like infinitely dimensional, so then it will be like infinitely dimensional matrices. When you map, right, you shouldn't, I would say you shouldn't think of this generators as acting on anything. They are just elements of the group. If you multiply them together,
it's just another element.
It's just another element of the group. And like
when you do the mapping to that, generate the group element of the group to some okay.
Okay, so let's look at this word. So this relation means that A and B commute. So we can commute A inverse and B inverse here. Now you see that two A inverses are now standing next to each other, and according to my mock relations, A squared is equal to the identity, so we can remove them. Now you see that now we have B and B inverse next to each other, so we can remove them as well. And we are left with ABC, but according to my relations, this is equal to the identity. So this word was equal to the identity. This word is equal to the identity. So this group word problem is actually not so trivial. For many groups, this problem is quite hard. And for some groups, it's even undecidable. And this complexity of this problem is actually what allows us to make our systems thermalize for such a long time. In some sense, our systems are kind of the time evolution of the systems there kind of tries to solve this problem. And since this problem is hard to solve, it takes a very long time to do this. So we can also visualize this this kind of word reduction process in a very nice way with a Cayley graph of the group. So if you don't remember what a Cayley graph is, this is Cayley. So in this graph, vertices are group elements, and then the directed edges between the vertices are applications of the generators or the inverses. And let's again look at these simple examples. So for the Z, this element is just the identity element. We can apply a generator and we come to the group element A. We can multiply it by A again. We come to the group element A squared, and we can do this infinitely. Or we can apply A inverse, which means going in the opposite direction to the arrow, and we will get A inverse and so on. So for the group Zn, for the cyclic group, we can apply A n times, and we have to come back to the identity. So the Cayley graph is a circle. Now for the group Z cross Z, the Cayley graph is a square grid where the blue arrow is the generator X and the red arrow is the generator Y. And you can see this relation as a small closed loop on this graph because XY is equal to YX. And this is a Cayley graph for the group D4. So I guess one lesson that I want you to learn from this Cayley graphs is that any word that multiplies to the identity is a closed loop on the Cayley graph. And the generators, the generating relations of the group, they are in some sense the elementary closed loops on the Cayley graph. So now let's take an arbitrary Cayley graph of some group. And let's take a word W that multiplies to the identity. And as I said, it corresponds to some closed loop on the graph. So for example, this purple closed loop. Now, how would we reduce this word to the identity?
I had a quick question.
Multiplies to the identity. Well, we can apply the generating relations one by
Hello,
one.
can I ask a
Each
quick
generating
question?
relation is an elementary closed loop on the Cayley graph. So we can deform it sequentially by subtracting elementary loops until we contract this loop to a single point. So this pictorial way of looking at it, actually, I think there is a question in Zoom. Can you repeat your question?
Yeah, hi, can you hear me?
Yes, I can hear you.
Yeah, no, I just wanted to ask, can you take linear combinations of words? And does that also give you a word like x, y minus y, x?
So yeah, no, we can't take the linear combinations of words because the word is in some sense defined through the group multiplication. So the group multiplication. So you just have only one operation in your system, which is the group multiplication.
Oh, okay.
Okay, so this pictorial way of thinking about this reduction process actually allows us to introduce the temporal complexity of solving this group word problem. So suppose we start with a word that multiplies to the identity. The question I'm asking is how many steps, and by step I mean a single application of a generating relation. So how many steps does it take to get to the identity word? And this notion is well known in the math literature, and it's called the Dane function. So colloquially speaking, the Dane function is the minimal number of steps that you have to take to transform W into the identity. But pictorially, we can write it as the area of a minimal surface that you can stretch onto this closed loop. So sigma is some surface, and then we require that the boundary of this surface is our word, and then we minimize overall possible surfaces that have this boundary.
I have one question.
Yeah.
So you are only considering those elements W that are equivalent to identity.
Yes.
Not some W prime.
Yes. So yeah, you can actually show that none of the scalings. So we'll now talk about how this Dane function scales with the length of the word. So you can actually show that none of the scalings of this Dane function actually depend on the like geodesic of the word, and the geodesic of the word is the shortest is like sorry. So what I'm trying to say is that it doesn't depend on the group element that word multiplies to. So I'm, for simplicity, considering only words that multiply to the identity, but you can ask, okay, maybe something is different if my words multiply not to the identity, but to some other group element. It turns out that the scaling of the function does not change. You can show this explicitly. So we define, so this was the Dane function for a specific word. We can also define kind of the Dane function for the group itself. It depends on some length L, and you just have to maximize. You just have to take like the worst case scenario. You just have to maximize overall possible words. Sorry, I forgot to put here overall possible words such that the length of the word is L. Yeah.
So is L the correspond? Oh, you just said L is the word.
Yeah. Yeah. So, and even maybe this was too abstract, but even relatively simple groups can have very large Dane functions. For example, this group, which will come back later, the Dane function for it scales exponentially with L. And if you slightly modify this group, then you can make it scale as a iterated exponential without. And if you modify it slightly again, then you can get something even more monstrous, where it's an iterated exponential where the size of this iteration scales as log of L. And maybe I guess you can cook up even more bizarre examples. So we can also talk about the spatial complexity. So sometimes in order to reduce a word to the identity, we first need to stretch it to a longer word. So suppose this was my gamma 0, what is my original word. It's a loop on a Cayley graph. I'm just not drawing the graph itself. And the only way, so it actually multiplies to the identity, but the only way you can contract it to a point is to first expand this loop to a bigger loop, and only then you can contract it back. To quantify this property, we introduce the expansion length. So suppose we have this reduction process. Let me call it a trajectory. And I will introduce the length of this trajectory, gamma, which is just the maximal length of the loop in this, during all the time steps in this trajectory. And then the expansion length would be just the length of the trajectory minimized over all possible trajectories. So if this was too complicated, then in simple words, a word W must be stretched to at least this quantity in order to be contracted back to the identity word. So that's what it means. Okay, so enough group theory. So let's go back to physics. Now we can turn this problem into a condensed matter system. So again, we'll take some finitely presentable group. And this, the relations, I'm just writing them as some words, W1 to Wm, that are equal to the identity. Now we consider a one-dimensional chain, and on each side we put one of the generators or their inverses or an identity element. So for example, if you had two generators, then your Hilbert space, your local Hilbert space would be just 5-dimensional, because you can either put A or B, or A inverse or B inverse, or the identity E, right? And now we have to introduce some dynamics. So we have to write down the Hamiltonian, and we do it in the following way. So there are 3 terms. The first 2 terms are universal for any group. Oh yeah, sorry, I forgot to say that we want to introduce the dynamics in such a way that the global, the group element to which the word multiplies is preserved. So we can do some local updates on our word, but only in such a way that the global group element is preserved. So what can we do? So the first 2 terms are present for any group. The first term is just if you have 2 identities next to each other, then you can create some generator and its inverse. So that's like a creation of charge and anti-charge out of the vacuum. Then if you have an identity and then some other generator next to it, then you can always commute them, because identity commutes with everything. So that's just the propagation of charges through the vacuum. And then the only non-trivial terms, which are different for different groups, they correspond to the application of the generating relations. So since according to our generating relations, for example, W1 is equal to the identity, if we encounter W1, like this short word, as a substring in our state, then we can just flip it to the corresponding number of identities, because this, as we know, does not change the total group element. And you write this for every short word from your generating relation words. And I wrote down a Hamiltonian, but we can actually, like, nothing really will change if we instead consider random unitary circuits or even just classical Markov processes. which just update the string. So yeah, let me introduce our kind of study case, the simplest group that we could come up with that has this interesting properties. It's called the Baum-Slug-Solitar group. It just has two generators, A and B, and a single generating relation, which is BA equals A squared B. So in the generating relation, you can see that when A hops from right to left across a B, it doubles in size.
Can you go back to the previous slide?
Yep.
In principle, this W1 to Wn will be infinite because you can combine with them. Two elements like an actual identity multiplied together is virtual identity. So
Yep,
how
yep.
do you truncate it?
You just fix it to whatever you want, because you want your Hamiltonian to be local. So of course you can write an infinite number of words that multiply to the identity, but you just fix it to whatever you want really. But maybe it's reasonable to fix it to truncate it to like the smallest presentation of the group that you can have. For example, in this case, in this example, we just have a single generating relation, so you cannot make it simpler than that. So yeah, how does this group look like? So let's try to construct its Cayley graph. So this generating relation, you can see it here. So if you multiply B by A, it's the same as multiplying A by B. So this is like a single rectangle where one of the sides is doubled. And then you can now glue, first of all, you can of course glue these rectangles on this B side, but you can also glue two similar rectangles to the bottom side of a big rectangle. So you can see that this graph has this hyperbolic structure. So once you go like down in the B direction, the number of rectangles doubles at every layer. But then this is actually not the only thing that can happen. This is not the full Cayley graph, because you can also take the same kind of rectangle, but you can shift it by like half of this, but by this distance to the left, and you can glue this big rectangle to this place, but now it will kind of go out of plane of the board. And so the actual Cayley graph looks more something like this. So you have like one sheet of the Cayley graph, but at every orange line, it splits into two other sheets. So and then here it splits again, and then here it splits again. So in some sense, it's like a binary tree, direct product with a real line. So like this is a real line, and then if you look at it from this side, you'll just see like a binary tree. Okay, so now let me actually show you that this group has the interesting properties that we need. So let me construct the following word, so you can see it written there, and you can check that it actually multiplies to the identity. And we can draw it on the Cayley graph in this way. So it goes n steps in the B direction, then it goes one step in the A direction, then it goes n steps back in the B direction, then it goes in the A direction again, and then it goes to a different sheet and kind of repeats the same pattern, but on a different sheet until it comes back to the origin. So the length of this word, you can just easily count. It's just 4n plus 4, where n is some parameter. But the area of this word, so the number of rectangles that it encloses, actually scales exponentially with n. So the Dane function of this word scales exponentially with the length of this word. And it turns out that you can show that for this group, this is actually the worst case scenario. So for this Baum-Slug-Solitar group, the Dane function scales exponentially with L. And also coming back to your question, even if we choose a random product state in this group, you can show that the Dane function for random words will scale as exponentially, but with a square root of the length of the word. So it's not exponentially, not like e to the square root of L, essentially, instead of e to the L. So in some sense, it also means that even random words in this group will thermalize for a long time. Okay, now how can we actually observe this? So this is where numerics is very informative. So we can actually see that this word thermalizes for a long time by looking at the local observable, which is the number of bees, because the number of bees in this model is a conserved U1 charge. Because you can see, so this is the relation again, you can see that the dynamics actually does not change the number of bees, because we have one bee here and one bee here. So if you think of B as like a plus charge and B inverse as a minus charge, then the total charge should be conserved. And we can look at the expectation value of B at every site evolving in time. And for this particular numerics, we consider a random unitary circuit. So we just apply updates on the string. So, okay, so these are the results, and let me explain you what happens here. So first look at the left. The x-axis is the space, so it's the different sites. And then this is the expectation value of B at every site. So it's like averaged over some short time window. So in the original word, let me maybe just quickly return to show you the original word. In the original word, we had a density wave of the B charges. So we had n plus charges, and then we had n minus charges, and then we had n plus charges, and then we had n minus charges again. So that's what you see in the numerics. So in the original state, there is a density wave of the B charge. And we time evolve it for some time. And at some point, it just collapses to a flat distribution. And you can see this on this plot. So we can also take square of this quantity and then average overall space. And that gives you this curve. So this quantity, this observable, is non-zero for some time until it suddenly collapses to 0, and then it stays at 0 for almost forever. So this is the same picture, but just a static one, where different different colors denote different times. And we can see how this scales with the system size. So
you must be averaging over some ensemble, and I didn't catch what ensemble you were averaging over. Did you say?
Yeah. So which exactly average do you mean? So here, okay, on the left, the averaging means averaging over a time window, like capital T. So we take capital T layers of the random unitary. And at every site, I average the number of bees over this time window. So that's the quantity that you see on the left. Now, on the right, we take this quantity, square it, also at every site. And then this long bar at the top means we average it over all spatial sites.
Now you have a Hilbert space of 5 states per site and length, 100 over 100.
Yeah.
How could you ever do that numerically for a unitary quantum dynamics?
No, sorry.
Sounds okay. Like that's not what you're doing.
Sorry. This is a single run, so I'm not averaging over any ensembles here. This is
right, but even a single run, why isn't it go to an incredibly complicated entangled state that you just can't follow?
Oh, yeah, because essentially, because your random unitary in this case, it's kind of similar to a cellular automaton unitary, because it does not create entanglement in the product state basis. So it does.
Okay.
It does.
So it's not a quantum system.
In some sense, yes.
Well, no, it's not a quantum system, right? It's a classical dynamics.
It's a classical, yeah. It's
Okay.
yeah, you can
Okay.
think of it as a random, as a classical Markov process. Yes.
Yeah. Okay.
Right. So, okay. So now we fix the initial density of B's to be something. So in this case, I just take m equals L over 10, and then I do the same experiment for different system sizes. And I record the thermalization time. By thermalization time, I mean the time at which this observable drops to 0. And we see that it scales exponentially with the system size. Now, yeah, we can, so this was about the temporal complexity, but now we can also ask, what about spatial complexity? So we can repeat the experiment, but now we can just fix the word. So we fix m, and then we pad the system with lots of identity sites. And we can ask the question, how does thermalization time scale with the number of these extra identities in the system? So the length of the word here is just 44, because we take m to be, I fix m to be 10. And then once I change L, you see that at large L, the thermalization time is roughly a constant, saturates to a constant. But then at short L, it starts diverging until at some finite length that is around 50, so it's greater than 44. The system stops thermalizing completely because there is simply not enough empty space for this word to expand, perform all the necessary dynamics, and contract back. And in particular, if you start with 0 identity sites, so if your L is equal to 44, then the initial state is completely inert. And this actually motivates us to introduce this notion of fragile Hilbert space fragmentation. So consider 2 words on a system of size L. So this S are generators. And then suppose we know that these 2 words multiply to the same group element. But if we just fix the system size to be L, then we cannot transform one word to another. But now, if we pad our system with the identity size, then you can actually connect these 2 words, one word to another. And yeah, so yeah, we call it fragile Hilbert space fragmentation because the fragmentation disappears if we are allowed to temporarily increase the system size. And then once all the dynamics is performed, we remove this extra space.
Small question.
Yeah.
Can I think of this as some super selection sectors in the Hilbert space?
Of what exactly?
Of like this word, the first one on the left hand side, maybe it's one of the block diagrams.
Right.
What is the block diagram? If you increase the system side, that you introducing some interaction between them.
Yeah, in some sense, yes. So it's, you have to be a bit careful because it's, so you have to make sure that this extra space remains in the same state after you've performed the dynamics. But yeah, you can think of it as, so you have your symmetry sector and it's block diagonalized into smaller Krylov sectors. But then they are these Krylov sectors are disconnected only if your system size is fixed to be L. And if you allow yourself to temporarily increase it and then shrink it back to L, then they become connected. And so the non-zero matrix elements appear between different Krylov sectors.
So assuming that we are restricting also to local modes.
Sorry, we are restricting what?
Only to local modes.
Yeah. Only to local moves.
Does it hold more generally that maybe there's a very far off off-diagonal elements sitting there if we allow random non-local moves?
Well, allowing non-local moves is tricky. It's tricky to figure out which non-local moves are allowed, because essentially, if you want to like flip something here and then flip something far away, in order to figure out whether this move is allowed, you have to know everything that's in between, because otherwise you will not be able to preserve the total group element. So I don't know. I haven't really thought about non-local moves.
Or about the single language?
Okay, and I want, so how much time do I have? Okay. So yeah, I want to just finish with like connecting this problem to something else. Like this is another project that I'm working on with Claudia, and we just suddenly saw an interesting connection between the two projects. Yeah, so there is a connection between this group word problem and the obfuscation of circuits in cryptography. Yeah, so this is what I'm working on with Claudia and Andre at BU. So we can consider a reversible classical circuit, and we can look at it as a 1D model where at each time step we only allow for a single gate, and then we denote different gates as different degrees of freedom. So suppose this C naught, I will call it A, and this naught I will call it B, and so on. And for example, here we have a naught, and here we have the same naught, so they are both B's. So now the question I'm asking is, can I somehow change the circuit such that it performs the same computation? So this might be useful. For example, suppose I created some software and I want to give it to people and let people use it, but I don't want people to see the structure of my code. I don't want people to know like how exactly my software works, but I want them to be able to use it. So, like my original code was some circuit with a very nice structure that, like, if you look at it, you see this structure and you see how how my code works. But I want to somehow obfuscate this circuit. So I want to somehow like mix the different gates in a very complicated way, but in a such way that the computation that the code performs would be the same. So I want to somehow scramble my circuit. So I can basically formulate it as one of these group word problems, because for classical reversible circuits, the group that these different elements form is a permutation group, S2 to the n, where n is the number of bit lines that we have. And I can essentially ask, can I introduce some local dynamics that kind of locally changes the sequence of gates in my circuit, but in such a way that the global computation that my circuit performs is preserved. Yeah, and so I also don't have time, and I don't want to go much into details, but there are some interesting questions one can ask about this, and some interesting results. Like, for example, one of the results that we recently discussed with Claudia is that there is like an if you try to introduce some local dynamics for this model, then you will necessarily see some fragmentation, and we can prove that you have to see this fragmentation, and if you don't, then like there would be some collapse of the complexity classes. For example, there would be like NP would be equal to co-NP or something like this. But I think, yeah, I guess I don't want to go too much into detail. So let me kind of conclude with some other stuff. So stuff that I didn't talk about, but that will be in the paper. So I didn't talk about non-group examples with similar properties. In particular, if we relax our condition, instead of groups, we consider semi-groups, then virtually any model with kinetically constrained dynamics can be kind of put in this framework of semi-group models. And then we can also generalize this models to higher dimensions. And in this way, we can actually construct a fairly generic class of models with Hilbert space fragmentation that's topologically robust, meaning that if you like put it on a torus or like on some manifold with like boundaries, then arbitrary perturbations will not mix different Krylov sectors with each other. And then some interesting future questions is, what are the ground states of these models and what are the entanglement properties of the ground states? And maybe it would be interesting to achieve some geometric understanding of thermalization. For example, if we take a random graph, then how should we think about thermalization in this case? Yeah, and I want to conclude my presentation on that. Thank you.
Thanks for the nice talk. Any question, including on the Zoom?
Can you go back to that slide of the fragmentation?
At the very beginning, or which one? Oh, this one. Yeah.
So this is very similar to the confinement deconfinement problem. So I'm just asking, have you like tried calculating the density of words that are for with respect to when you increase the word size?
You mean the So you mean the number of words that multiply to the identity with respect to I actually have
I think that there's assuming an almost uniform density. What's happening in the first case is that the distance between two words that are equivalent to the identity is more than how much locally the jump we are allowing. And when you're adding more words, then the distance between two words that are equivalent to the identity is within the length scale of local interactions.
Sorry, so what's what's the question?
Yes, so the question is that to study the density of the words that are equivalent to the identity with respect to increasing length size.
This is very well. Yes, this is the fraction of words in the identity sector in the whole Hilbert space.
Yeah, this was what I was saying.
You can actually show, you can actually do some analytics and show that the scaling has to be, for example, here it has to scale as exponent to the minus L to the 1/3.
Yes.
So this sector, in some sense, so what this graph says is that in the thermodynamics limit, this sector occupies vanishing fraction of the whole Hilbert space.
Just one more question. We do something very basic, like probably when you started to study of the graph that knows to be product states. We're not talking about mechanical states here, right?
Well, so as you can ask a question. So what I presented today was essentially a classical Markov chain dynamics in a classical Markov chain. So you just do classical updates on your string. So this was the question of David. David asked the question on Zoom. You can also ask what happens if I actually consider continuous time evolution under the Hamiltonian that I wrote on one of the slides. And you can show that in this case, you can kind of define a hidden time. And the hidden time is, suppose you start in a product state, and then once you allow your system to time evolve, you will immediately, after infinitesimal time, you will have weights on all of the product states in your Hilbert space. So you can kind of look at some equilibrium distribution of these weights, and you can define the hidden time by asking the question, okay, at which time does the weight on some target product state reaches a certain fraction of this equilibrium value, and then you can show that the Dane function of the group will actually also kind of define the hidden time under the continuous time evolution of the system.
I have a question about fragmentation. So here it's something like that once you add ancillas, and fragmentation will disappear. Is it similar to the Scott problem where you enlarge the Hilbert space dimension per side, or sometimes maybe just introduce longer range open trains and then the scar might disappear?
I think it might be similar, because yeah, suppose you increase your interaction range in the system. Well, it's obvious that if your interaction range is L, then these two states would be connected because you can just flip the whole state immediately. So I think you're right. So there is some connection, but once you increase interaction range past some critical value, then these two states become connected.
And the reason you call it fragile is similar to fragile topology.
Yes. Yes.
Well, any other question?
Yeah, so let's say using your folder, if I do this is like so this will have been more days when I try to slow it down. That's what I want. Let's say.
Yeah.
If I only ask you, this is what's the fastest?
Right. So I guess your question is, can we choose a group that would thermalize very fast? Yeah, no, the fastest, so for a given group, the fastest thermalization time is actually the Dane function. That's how we defined it. That's like the minimal number of steps you have to take to reduce the word to the identity. So if you give me a group and a specific word, then the thermalization time of this word is defined by the Dane function. Now you can also ask a question, can you construct groups which thermalize very fast?
Yes, that's
and I mean, in some sense, this would kind of be like generic systems thermalize fast. So in the group language, if you take any finite group or any abelian group, then they would thermalize very fast. If you think about abelian groups, then like everything you have to do to thermalize a state is to just like commute all the generators past each other. So they will just kind of like ballistically propagate and then annihilate with their inverses in. Yeah, it would just scale with the length of the system. Exactly. Yeah. You can actually show that for any finite group, the Dane function is linear in L. Even for non-abelian finite groups.
Question.
Yeah.
So this is about the comment that I think David Hughes made during a little bit earlier, that you're not working with a quantum system. And I just wanted to understand, like, I mean, because you have a Hilbert space and you have unitaries and everything. So in what sense is this not a quantum system?
In what sense? Okay, so it's not a quantum system because what we do here is a random unitary dynamics, but now, like, which unitaries do we allow? We allow unitaries that preserve the global group element. And what does it mean is that the unitary is essentially replacing a sequence of letters with a different sequence of letters. So this unitary is actually kind of like a classical update.
Right.
So the you can look at the actual dynamics that happens as just a classical update of a string to a different string.
Right. I mean, so you have a sort of your unitaries are discrete, right?
Yeah.
And but I mean, don't you still have all the other aspects of quantum mechanics, superposition, and so on and so forth?
Well, if you consider a random unitary like this, then you do not create any entanglement in the states. You will create entanglement in the operator language, in the sense that if you start with a local operator under this dynamics, it will spread.
Okay.
But like I was answering the question earlier. You can, instead of considering a random unitary circuit, you can consider a truly continuous time evolution under the Hamiltonian that I wrote down. And then you can also show that the hidden time in this time evolution is also basically defined by the Dane function of the group.
Okay. I was trying to find a reference online, but I couldn't find anything. Is this paper yet to come out?
Oh, yes, it's not out yet, but it's gonna be there soon. Yeah.
All right. Thank you.
Sorry, just a curiosity. Before you said that you can create also graph in which you have this Dane function that is scaling more than exponentially faster.
Yeah.
How should I interpret that quantum mechanically? It means that the spectrum, so that you have the Heisenberg time that is scaling more than exponentially, so you have kind of a degeneration of mini gaps. Probably I'm not clear enough, but can you comment on that? So physically, how should I interpret that? Because essentially it's meaning that also the Heisenberg time is super huge, no?
Yes.
From quantum mechanics, no?
Well, yeah. So I guess maybe the explanation that I can provide is that your Hilbert space has such a connectivity that there are states that are kind of like trapped in far corners of the Hilbert space. So in order to reach a bigger, more connected cloud of states, which kind of defines all the equilibrium properties of the system, it has to like, the state has to essentially find its way out of this far corner of the Hilbert space. I'm not exactly sure what this means.
So should they think this one really as a typical quantum system, because the connectivity is not L, but maybe, I don't know, there are some states where it's even not scaling with system size. So it's really like
well, it's not it's not a typical quantum system.
Okay. And you can do it still locally.
Yes. Yeah, everything is local. Yes.
That's interesting. Okay, thank you. It was just a curiosity. Thank you.
Any other questions?
Yeah, probably we can stop here and we can continue discussion. And let's thank the speaker.